Good afternoon, everyone. Welcome to another session of a network seminar series hosted by the Center for Network Intelligence at the Robert Bohr Center for Cyber Physical Systems, IISc. Today's talk is by Dr. Parthe Pandit, and he will be speaking on exact analysis of generalization error in generalized linear models. Dr. Parthe Pandit is a Simons postdoctoral fellow at the Halle Gioli Data Science Institute at University of California, San Diego. He obtained a PhD in ECE and MS in statistics, both from UCLA, and a dual degree in EE from IIT Bombay. He is a recipient of the Jack K. Wu Student Paper Award at ISIT 2019. He has also been a research intern at Amazon and Citadel LLC. Before we move on to the talk, we would like to request the audience to subscribe to our YouTube group for information on future talks. You can also visit our website for more details. Finally, we request the online audience to keep your microphones on silent for the duration of the talk, and for questions, you may ask Dr. Pandit directly. For the in-person audience, we have arranged coffee at the coffee machine. Please help yourself to continue conversation over coffee after the talk. Over to you.
Can everyone hear me on Zoom?
We're checking.
Thanks for the kind introduction and also for the invitation to give this talk. Today I'll be presenting some work I did during my PhD at UCLA, which is about characterizing the generalization error in GLMs in a certain high dimensional regime. So this is work in collaboration with some wonderful people. Melika is a grad student at UCLA. Mustafa also was a grad student until recently and he's moved to Google. Ali Fletcher was our advisor, and also Sandeep Rangan, and Phil Schneider was our collaborator. So the title was Exact Analysis of Generalization Error in Generalized Linear Models. That's a mouthful. Let's try to parse those things one by one. So generalization error. This is an object we all care about in machine learning a lot. So here is typically what happens in machine learning. We are provided several samples of training data, and using this training data, I'm considering the supervised learning setting. Using this training data, which is drawn from some distribution, you train a model or a predictor or an estimator. Let's call that f hat, which belongs to some model class here, H. And using the estimator that you've learned, you want to be able to make predictions on previously unseen data during the training process. Okay, so that's what we call test data. And we want to have some understanding of what is the probability of making an error, or in general, there could be other different metrics of error that we may be interested in. And that the fact that we have not seen this data is what makes it generalization. And in general, we could have a setting where the test distribution is different from the training distribution. And if there is some kind of a mismatch between these distributions, we would like to know what kind of degradation do we see in the generalization error because of this mismatch. And these are kind of questions that we all think about in machine learning all the time. So let's just quickly look at generalized linear models now. Before that, a simple introduction to linear models. We have some targets that we're trying to predict. And we posit that they're related to the features or the inputs as x transpose theta, where theta is some unknown parameter, and we want to learn this parameter theta. Okay, so this was the linear model. Generalized linear models are just a simple extension of linear models. One of the limitations of linear models is that they naturally assume that the target variable can take any real value. But in general, we may be interested in predicting targets which are not real value, and they may belong to a specific subset of the real value. And so this function p is essentially
Should we call Jassim or is it? Continue.
Okay. Yeah, so essentially this function p is doing some kind of a mapping from the real line to whatever domain that this target belongs to. Yeah. So some examples are, if your targets are plus or minus 1, then essentially some function like the sine function does this operation of converting a real number into plus or minus. Notice the variable psi here is some kind of a noise or a nuisance variable that we don't know during training. If you have some bounded domain, one usual choice of doing this compression from the real line to a bounded domain is a tan H nonlinearity. There's also a probabilistic interpretation of what generalized linear models are. So the idea there is you say that the targets are samples from some distribution, P mu. This could be an exponential family distribution, for example, and with the mean parameter mu. And the idea is that some function of this mean parameter, g of mu, is again a linear function of theta and of x. Okay. So this function g is called a link function, and it's usually an invertible function. And the way it's used at the time of predictions is once you learn a parameter theta hat, you take an inner product with a new sample x, and then you input that to G inverse. Okay, and that's going to be a prediction for y. Okay? Once you have learned a parameter, you make a prediction y hat in this manner. So here are some examples of GLMs using this probabilistic interpretation. So if y is normally distributed, then this is simply the linear model. But if y is a Bernoulli distribution, so it only takes values 0 or 1, where p is the bias of the Bernoulli random variable, then the way it's related to the inputs is usually using some logic transformation. Okay. This is a really flexible framework, and the first thing that someone would do on a new data set is usually a generalized linear model kind of a fit. So
is there a one-to-one relationship between this left-hand side and the right-hand side? For the normal is clear, right? Psi is the Gaussian.
Right.
But for say Bernoulli and Poisson.
So this model and this model, there is a one-to-one relationship. The tan H and the Poisson are not related because the domain of the Poisson is positive integers, whereas the domain of the range of tan H is.
So is there one, or it just doesn't matter? Just came up with a distribution.
Yeah, usually there is a distribution of choice that somehow naturally comes out of the application you're looking
at. I just don't see directly because I was thinking, is there a function and a noise model which lead to the Poisson distribution for y? So I'm saying, so is there a phi and a psi which will lead me to have a Poisson?
I guess you can always have phi be a sampling function from the Poisson distribution in this manner.
Let's continue.
Okay. So here's an example of GLMs in signal processing. So suppose you're interested in reconstructing an image X from certain quantized noisy measurements of the image. So this P is some quantization operator. AI are some linear measurements of your image. Then the problem is you don't know X, you know Y, and you know AIs. Okay. Usually, if the problem is for an image, then you usually are interested in some transform domain coefficients of the signal, and you would fit in the transform domain directly using some kind of an optimization problem. This is just an example. I'll talk more about how to fit GLMs more generally. How do GLMs come about in modern contexts of machine learning? So specifically, neural networks is what I mean by modern here. So there are two examples. So first one is transfer learning. So what we do in transfer learning is you pre-train a network on a certain task where you have lots and lots of data, and then you want to transfer a model that you've learned onto a data set that is somehow closely related to the data that was used for pre-training the model. So you learn a pre-trained model, and then you remove the last weight of the last layer of this network, and you retrain only the last weight of the last layer weights of this network. Okay, so again, that's implicitly assuming a GLM where there is some feature extraction step until the penultimate layer of your pre-trained network, and then there is a last layer that you're going to learn again. Okay. Another context is kernel learning, which is now very a topic of interest again in the deep learning theory community. There is something called a random feature map that some kernels have, and you can write a kernel between two inputs as the inner product of some feature map of your input. Okay, and when you're fitting a kernel in using a random feature map, you're again implicitly assuming a GLM of this form where there is some kind of a feature transform and then a linear model, and then a nonlinearity applied on top of that. Specifically in the context of neural networks and the connection to kernels, the specific feature map is what is called the gradient feature map, and the kernel that comes out of it is the neural tangent kernel. I won't talk about this more at this point. But these are some problems I've been looking at these days.
So what is random here again?
The randomness is incorporated inside psi. So you can think of it as you multiply by a random matrix.
Okay.
And then
phi has some inherent randomness.
Right. Yeah.
So the kernel output will remain random, right?
It will remain random on the feature map that we just took. Yeah. But it's a fixed randomness. Once the randomness is chosen, you don't quite change what that randomness is.
So you have ensemble of randomness and you pick one of that from that, and then you apply it here. Is that?
Yes. And that ensemble converges exactly as the size of the ensemble increases exactly to what kx explains. And the approximation comes from the fact that you're choosing one sample from this.
I mean, I'm using some kind of log number, but what is the larger?
Exactly, yeah.
What is larger is the feature space? Is that?
The feature space is large. Okay, so how do you fit a GLM? Predominantly, the most popular way of fitting GLMs in the context of high-dimensional signal processing problems and in machine learning specifically is via an optimization procedure. So usually we are interested in theta hat, which is the proposed estimator, as the solution to a minimization problem, which involves a linear combination of two terms. The first term is a loss term, which measures the data fitting capabilities of a proposed theta, whereas the second term is a regularization term, which measures some kind of a structural property that you are looking for out of the estimator that you're choosing. Okay. There is a probabilistic interpretation here again that this is essentially some kind of a map inference where you're interested in the mode of the posterior distribution P of theta given y, which is proportional to the likelihood distribution P of y given theta times the prior, which is P of theta, which has lambda as some parameter. And you don't quite care about the normalization factor because it doesn't depend on theta. And that is one of the main reasons why optimization is the most favored approach for fitting a GLM in high dimension. There are also several other ways of fitting GLMs, like Bayes estimation, which involves taking the mean of this distribution instead of the mode or the method of movements. But today I'm going to be focusing only on the optimization way of fitting a GLM. And specifically, I'm going to be concentrating on loss functions which are separable in this manner and regularization functions which are also separable in this manner. Okay, so some examples are some kind of an empirical risk minimization with a penalty like the ridge penalty or the L1 penalty are all examples of this kind of a fit. Now, the problem of interest is going to be in the setting where theta is high dimensional, which means that the size of theta, the number of free parameters in theta, are not negligible compared to the number of samples that you have for training. So n is the number of samples and p is the number of parameters in theta. Okay. Now, a statistician at this point has several choices that they can make as to what is the choice of the loss function, what is the choice of the regularization function, what is the choice of the regularization parameter.
So I'm not still clear what is fitting a GLM means here. I mean, I understand the optimization question. What do you mean by fitting a GLM?
Yeah, so fitting a GLM is come up with a theta that you would use to predict the unseen data.
So, but that is just finding the theta. You already assume the model, right? You already assume that there is generalized linear model.
Right.
So you're assuming you already know some phi and you know the choice of the psi, right? The only thing is to find the right theta.
Correct.
Correct?
Yes.
Okay, that's what you call fitting a GLM. Okay.
Correct. Yes. So I'm again going to stay in the setting where there is a well-specified model. In general, in practice, people work with misspecified models as well, just to get a baseline of what things look like if you just fit a GLM. But for the sake of analysis, let's work with a well-specified generalized linear model. So yeah, as I was saying, we're interested in the effect of these design choices that whoever is going to solve this optimization problem has to make before even solving this problem. As to how does the choice of all of these loss functions, regularization functions, and lambda affect some kind of quality of this solution, theta. What I mean by quality of the solution, I mean some kind of a performance analysis is what you're interested in. So if there exists, I'm going to assume that there exists a certain ground truth theta star for the sake of analysis. And I want to understand maybe certain parameter estimation errors on theta hat with respect to theta star. These could be in any norm that would be of interest to the application that the scientist is interested in. In machine learning specifically, we are interested in some kind of a generalization error, which involves an expectation with respect to the test distribution. And again, the metric could be different based on the application you're interested in. We want to develop a methodology that's flexible enough to allow the statistician to choose their metric of performance analysis. Okay? And in general, this metric could be very different from the loss function that was used to train this GLM. So loss function choices are usually based on computational considerations, whereas metric choices are based on certain interpretable performance metrics like F1 scores and so on and so forth. So yeah, as I said, we want to develop a methodology that allows the statistician to choose this metric independent of the law.
So if the training metric is different from the error metric, isn't there a mismatch? Like you're training a data on a different metric, but you're evaluating on a different metric. So
yes, but we do that all the time. So there is a mismatch, yes, but that's often what we are interested in.
But shouldn't they be the same? Like,
not necessarily, because you may be interested in a different performance metric than what you used to train.
But won't that result be like it's naturally just a bad idea? Won't you want?
Well, I can give you an example.
Maybe not the same, but you would think that. So what I want to say is the following: suppose I'm going to test on this metric psi, right? To see your generalization, and because you have regularized it, I know that maybe just putting psi there is not a good idea, but there exists maybe psi star. For this psi, maybe there exists psi star. If you put in loss function, that would have been the best choice. Hypothetically speaking, I don't know what that would be.
Right. So maybe I'll give you an example where this kind of a thing actually occurs in practice. So often we are interested in probability of error, which means psi is the indicator function, whether or not y hat is equal to y. This is an extremely discontinuous function. You cannot do optimization using this function as your loss function. And so we often use other proxies that some kind of approximations of this as the loss function during training. So the logistic loss or the hinge loss are certain examples of approximations we use during training because they are friendly from an optimization point of view. But at the end, what we really care about is a probability of error, right? So in that sense.
But they're still motivated by that, right? I mean, those loss function are sort of trying to approximate it by continuous function.
That's right, yes.
So
but they're not the same. Right?
Yeah, no, it's true, it's true, but still it's trying to approximate that, right? It's not arbitrary that I just chose one here and another one there. It's still trying to approximate the performance metric which you're interested in.
Correct, yes. Yeah, so just a few comments. This kind of an analysis is extremely hard and very expensive because you have to usually bring in some domain-specific knowledge or the problem-specific knowledge to be able to do some kind of analysis of this sort. It's also complicated by the fact that we're working in high dimensions, where the number of samples is not too large compared to the number of unknown quantities in the model. And in certain high-dimensional settings, this is what I mean by high-dimensional settings. Statistical consistency may be too strict of an ask from the procedure itself. So can we get some kind of an analysis when statistically the estimator may not be consistent, but there's still a bounded performance metric for that estimate. To complicate matters even further, we may be interested in non-convex and non-smooth optimization problems. And this makes the analysis really hard to do just because, well, optimization itself has some limitations when it comes to handling these kind of relaxations from the standard things that are looked at. And essentially, the main hardness of analysis comes from the fact that we rarely know the estimator as a closed form function in terms of all the different variables in this estimation process. So things like the training distribution, N, P, the choice of the regularization parameter, the choice of the loss function, the choice of the regularization function, and whatever was generating your data, let's say theta. It's very rare that you actually have a closed form expression, and so doing a direct analysis becomes unclear how to even go about doing such an analysis. Okay. And the kind of questions we are interested in is you want something that is really general, but there are several hurdles that you want to overcome. Can you do that? Can we understand performance under certain random problem instances? If not under the most worst case analysis kind of setting. And that's exactly what I'm going to talk about today, which is exact analysis in high dimensions. So on a very high level, the idea is the fact that you want to leverage this property that you're really in high dimensions. And high dimensional systems that have a large number of degrees of freedom that are random behave in a certain deterministic manner. Okay? So this kind of this property has been exploited a lot in science and engineering over the last several decades. Essentially, if you're thinking of a gas inside a container, there is a lot of activity happening at the molecular level, but that's not what's important for a mechanical engineer trying to design an engine using this gas. There are some macroscopic quantities like pressure and volume that we work with when designing engines. Similarly, in electrical engineering also, we work with objects like current and voltage, which are also themselves macroscopic quantities and not about what happens at the minute level of an electron. So the next natural question is there something analogous happening in machine learning as well? can we come up with some such macroscopic descriptions that are concise when it comes to describing what's happening in the estimation process as the entire procedure is to be analyzed? Okay. And turns out there is, when you look at it from the right angle, you can actually get some insight about the estimation process in a very precise manner, using this same idea that large random systems have a concise macroscopic deterministic behavior. Okay. And this work that I'm going to present is based on a line of work that was started by David Donahoe and co-authors in 2008, and this has become a really burgeoning area of theoretical work, which is motivated by some ideas from statistical physics, which essentially uses what I've been saying again and again. So there are some new developments in random matrix theory that also makes some of these arguments really precise and really rigorous. So the results I'll be showing you today are also rigorously proven in theory. And the nice thing about this entire analysis is this is a completely different technology than what is usually used in optimization-based analysis. This does not rely on any kind of convexity assumption. And so this allows us to broaden the scope of problems that we can analyze, the procedures that we can analyze. Okay. So here is to give a high-level view of what kind of regime of statistical analysis we are going to look at today. So on the x-axis, if I plot the n, which is the sample size or number of knowns, and on the y-axis, the model size or the number of unknowns, then the classical statistical analysis lies in this regime, where the model size is at most logarithmic in the sample size. There are a lot of nice results about what happens to optimization-based estimators in this regime. So things like asymptotic consistency of the maximum likelihood estimator, asymptotic normality of the maximum likelihood estimator. This is something we all study in detection and estimation theory classes. On the other hand, there is the hard regime, where if n is O log p, then information theoretically things are hard. You just can't do estimation unless you make a lot of assumptions further about the structure of the problem. A lot of work has gone in the last 2 decades about how to do analysis in high dimensions. A lot of really nice and cool results have come out about non-asymptotic finite n finite p analysis of optimization-based estimators. So ideas in compressed sensing really lie in this regime, and they're really powerful qualitative results. But today we're going to focus on a smaller regime. We're going to look at what is called the proportional regime, where p and n are both growing at the same rate. Okay, so I'm going to look at the asymptotics in this regime. So p is going to infinity, n is also going to infinity, but the ratio at which they go to infinity is some constant. This constant can be less than 1, greater than 1, any number between 0 and infinity. Okay. Now, one of the challenges of the non-asymptotic regime is that there are several large unknown constants, and as a result, the theory that we get is a little hard to use directly in practice. The focus of most of these results is to get an understanding of what is the landscape of problems where consistency is possible, statistical consistency is possible, and they do a good job at giving us a qualitative understanding of what those regimes are. By staying in this proportional asymptotic regime, however, we get very exact and precise answers. There are no large unknown constants. At the same time, even if there is no statistical consistency, we can get a good handle on what is the error that you're going to pay a price for. So we often do statistical estimation even though the estimator is not consistent. But what is the price that we're paying in that regime is something we can now get some characterizations for when you stay in this regime.
So is the inconsistency due to the fact that you are working in that regime?
Yes. So there are some problems which are just inconsistent when you work in this regime. We want to know exactly how inconsistent. If the inconsistency is not too bad, we can live with it.
And is the parameter p under your control? Or
Not quite, but we want to understand from an analytic point of view what happens when P increases if you keep N fixed. Yeah, does that answer your question? Or
so P is the number of unknowns, right? So
P is the number of unknowns.
That depends on the model that you have. So
correct. So I'm not looking at a specific model. I'm looking at a sequence of models. Yeah, that's the kind of analysis I'm going to be looking at. It's not about a single model like you would do during classical statistical analysis. So here is a teaser of the kind of results you can actually show. So this is an estimator called the multitask lasso estimator, which is a group lasso kind of an estimator. This is an estimator for a matrix problem, and the estimator is highly nonlinear in all the objects that are involved in the design process. And there is no closed form expression for what the estimator is. In spite of that, you can actually get a closed form expression for what the asymptotic mean squared error of this estimator is with respect to a certain model for the ground truth. Okay, I can write down exactly what this is. So this is an equality, and there are no unknown constants in this equality. These functions f and u are also known in terms of certain special functions called the upper incomplete gamma function and the gamma function, which are actually part of the SciPy library. And these are all the different kind of design parameters that this problem has that a statistician would care about. Things like signal power, signal sparsity, noise power, and so on. And what we see here in this plot is that this is the theoretical prediction that we get by just plugging in whatever this function is. On the x-axis, I'm varying lambda, which is the regularization level. These colors are different levels of sparsity in the problem. But what's really cool is that these are experiments on finite n and finite p, where p is something like 1,000. And in spite of just being 1,000, the infinite prediction is very accurate. So yeah, this I think is really remarkable. I'll maybe talk more about this a little later, but this is the nature of the result that I'm going to be talking about today. So here is an outline for the rest of my presentation. I'll briefly characterize what the generalization error is in some functional form. Then I'll give some examples of exact analysis under several different GLM models that are commonly used. And then finally, if there is time, I might talk about the analysis framework that we use, which is based on vector approximate message path. So let's look at what the characterization of the generalization error is. So here is my data model that I'm going to use for this analysis. So there is a generative model for the labels. Okay, so y is related to x using some ground truth, which is theta star. This is known only at the time of analysis, not at the time of solving the optimization problem. But it's a fair assumption because we are only interested in analyzing this estimator. This theta star satisfies this assumption that each coordinate of theta star comes from a certain distribution. Let's call that T star. And the noise variable also satisfies the same. So there are n instances of this noise variable, and they all are drawn IID from some noise distribution. Okay. I'm also going to make an assumption about what is the distribution of the features. So this is a simplistic version of the real set of distributions we can actually handle. This kind of makes my life easy to present. But the X train is the distribution of the training features, and X test is the distribution of the test features. I'm assuming right now that they're both drawn normally with different covariance matrices, sigma train and sigma test. Okay. And there is a distributional mismatch, so they can both be different covariance matrices, which means they're from different distributions. But I'm going to assume that these two matrices commute with each other. And I'm also going to make an assumption about what are the eigenvalue distributions of these two matrices. So these eigenvalue distributions converge in law to some joint law mu. Okay. So an example of this joint law is that they're both drawn from a log normal distribution. And let's say rho is some parameter I can control, where rho equal to 1 means that there is no mismatch between the train and test distributions, and rho less than 1 is basically some kind of mismatch between the train and test distribution. So here is the result. Under this data model, there exist two scalars, gamma and tau. These are two scalar constants, gamma and tau, such that this statement holds. Okay, so this statement is a little verbose. I'll just parse this slowly. I'm interested in some metric psi. I'm going to take the average distortion between the estimator and the ground truth. This is a random object on the left hand side. This depends on the training data. This depends on theta star itself. Okay. But as p and n both go to infinity, this randomness sort of averages out, just like in the strong law of large numbers. And what you get is actually an almost sure convergence to a deterministic quantity, which has a complicated functional form, but it's the expectation of the same distortion function psi. The expectation is with respect to two random variables, A and B. A has the same distribution as P star, and B has the distribution which is Gaussian with a variance tau. There is some other function involved here, which depends on the regularization function and the regularization strength. So this is just a functional form of the result. These quantities gamma and tau would depend on all the different design choices that the scientist would make. You would have to do some algebra going from this point to actually get an answer of what is exactly the mean squared error, or what is exactly the average distortion with respect to psi. But that such a convergence exists allows you to only work with scalar objects from now on and stop worrying about what's happening in the large high dimensional case.
Can you compute these three constants?
You can actually compute these three constants. They are actually very complicated, but in some cases you can actually just have a closed form expression for what these constants are in terms of the different choices.
And where does M appear?
Right. So M is part of the corollary of this theorem. So this was about parameter estimation error. A corollary is about the generalization error, which is what we care about in machine learning. So again, if there is some distortion with respect to the test predictions and the test labels, then as n and p go to infinity, there again is here an expectation with respect to three random variables now: z hat, z, and psi. And each of these has the distribution that's given at the bottom. So M is actually the covariance matrix of this bivariate Gaussian distribution. And M again depends on the different design choices that you would make during the estimation procedure. The interesting thing again is that this is a conditional expectation. So this is actually a random variable on the left hand side. But as n and p go to infinity, that randomness somehow seems to disappear, and you get a deterministic answer for what your generalization error is. So let's look at some examples of using exactly the result that I showed you. So let's start with a simple example, which is linear regression. So you have a linear model, and your generalization error is going to be just the square error. And I'm interested in a certain estimator called the ridgeless the ridgeless regression estimate, okay, which is this, the minimization of this objective function. Turns out it actually has a closed form expression. And I'm saying ridgeless because I'm interested in the limit where lambda is 0 plus, so very close to 0. So on the x-axis, what I'm plotting is the ratio of n and p. The dots are for experiments conducted with p equal to 1000, whereas the line is the theoretical prediction, assuming n and p are both infinity, and n over p is exactly what is the x-axis. Now, the behavior on the left side of this line, which is, so on this side of the line, n is greater than p. On this side of the line, n is less than p. So this is the over-parameterized regime or the under-sampled regime. And recently, we've seen some very strange behaviors in machine learning that have been observed in this regime. And that is what is called the double descent behavior. We don't quite need to go into the details of what this behavior is right now, but the main point is that we have a procedure that actually tells us what you should expect to happen for a finite experiment in this setting for a random problem instance. Okay. Now at this point you might say that, okay, you said that theta hat doesn't have a closed form expression, so it's going to make analysis tricky, but there was a closed form expression here. The next example is going to be, I kind of skipped something, sorry. So you can also do this analysis for the case when there is some kind of anisotropy. So your features are correlated with each other. And there is also certain mismatch between your train and test distributions. In all of these three settings, we still see that our theoretical model is very accurately able to predict what happens in finite sample experiments. Okay. So in the logistic regression model, we assume that the generalized linear model is exactly this here. Y given x is a Bernoulli distributed random variable with p, which is equal to the sigmoid of the features transposed with some ground truth theta star. And the estimator here is your logistic regression estimator. And the generalization error now is using a metric which is different from the loss that was used. So the metric is probability of error. And even in this setting, now you, however, don't have, even though this problem is convex, you don't quite have a closed form expression for what theta hat is in terms of the different values of lambda that you might choose. And we can very accurately predict what you might expect for a random problem. Again, this was still a convex problem. This analysis goes beyond convex analysis. And so if you're looking at something like tan H regression, where you use this kind of a loss function, which is not convex in theta, you still are able to predict very accurately what will happen in a finite sample experiment. Let's look at another example now related to the multitask lasso estimator that I talked about. So here in the multitask regression, what we're interested in is predicting k different tasks using the same set of features. And now the parameter is going to be a matrix valued parameter. In signal processing, this problem is often called multiple measurement vector estimation. And essentially, we are often interested in a setting where there are only few relevant features. So the ground truth theta star is somehow sparse in terms of how many rows of this ground truth are non-zero. So there are very few non-zero rows in the ground truth parameter. Now this is the group lasso estimator where there is a data fatigue term, the square loss, and a regularization term, but there is no square here. So the lack of the square kind of couples the rows of the optimization problem. Okay, so there is row coupling happening, the column coupling happening because of the first term, and row coupling happening because of the second term. So you can't solve the problem individually, you have to solve it for the whole matrix together. There is an implementation of this in scikit-learn, and we actually see that our predictions for what is called a Bernoulli-Gaussian model for the ground truth parameter theta star are again very accurate for finite sample experiments. So the theory here, the theory lines here are the complicated expression that I showed you very early on in the presentation. So yeah, I have that expression here again. We don't need to go into the details. What you can do, however, using this expression now is plot what is the best value of the regularization parameter lambda versus what is the sparsity in the problem, or the sparsity in the ground truth. And this is really cool now because you can actually tune the hyperparameters even before you can, without having to do some kind of cross validation experiment.
So how does increasing this lambda help you when sparsity is larger?
When you increase lambda, you penalize the regularizer more, and that enhances how sparse your proposed solution is. But it's not a linear relationship, as you can see from this code.
So all these results are for random theta star, right?
Random theta star and random x as well.
So are there any regions in the theta star space where these results might be very off, right? So on an average, you are saying that these are the results that can hold.
Right.
But there could be some regions where
there could be regions.
So is that phenomenon observed in these problems?
No. So these are kind of like typical regions in the space that we're looking at, because each coordinate is kind of independent in the ground truth. If you have a lot of structure in the theta star, let's say you're kind of looking at a really structured theta star, your ground truth is really structured, then these results may not hold.
Right. But typically, like, there can be a set of measures 0 where in the theta star space,
correct,
where predicting theta star is very difficult, right? So for almost any theta star that you can pick, you can predict it easily, but that could be a small subset where
correct,
the prediction is not easy.
Yes,
maybe due to some singularities or whatever.
Right. So that doesn't come out of this analysis, unfortunately. Yeah. A similar analysis you can do for multi-class classification, which is often a problem of interest in machine learning. So the standard way of solving multi-class classification is using some cross-entropy minimization. But recently there has been some work which basically says if you just do square loss minimization with the same penalty, just make sure that you are rescaling your targets appropriately using some hyperparameter R. You actually get the same performance whether you use the square loss or the cross entropy. This was a paper in last year's ICLM. The natural question is, what is R? How do I choose R? Right? This is some work in progress. Hopefully, I'll have something to say in a few months. But these are the kind of questions you can now answer using this particular framework that I've presented so far. So I'll very briefly go over the analysis framework, which is vector approximate message passing. Essentially, this is a framework designed to analyze map inference for a structured set of problems. Okay, so the kind of problems that this framework can address are of the following form. You have this kind of a setup. You have a Markov chain which is of the following form. Some Z0 multiplied by some unitary known matrix, giving you Z1, and then some element-wise operation which could be random, giving you Z2, and such an alternating set of operations. And finally, you get some observation Y, which is known. And the problem, the estimation problem, or the inference problem, is to find out what is unknown, which is the ZIs in this problem. Okay. So VIs are known unitary matrices, and SIs are some element-wise operations happening from taking a vector and making an element-wise operation to get another vector. But that element-wise operation could have some randomness. And this is a Markov chain because essentially, it has a chain structure, as you can see. If you want to do map inference on this, this is equivalent to minimizing a chained non-convex cost function, which is essentially the posterior distribution P of Z given Y. Right? You just use the Markov chain property and get this expression. And then you have some constraints that couple Z1 to Z0 and Z3 to Z2, and some likelihood functions of the form Z2 given Z1 that come out of the randomness from these element-wise operations. Okay. So notice that each term in this objective function is separable over the coordinates of whatever the estimate is. At the same time, each term involves only two consecutive variables. So this term and each of these two terms involve consecutive variables, two variables at a time only. And essentially, vector AMP is an analyzable algorithm for solving these kind of estimation problems. It proceeds essentially in a divide and conquer manner, where you solve successively some simpler minimization problems involving only two variables, and these are called proximal operators. And these are simpler because proximal operators have a certain property that if the this function is separable, then the proximal operator is also separable as a function of R1 and R2, which are some quadratic penalties as part of the operator. And essentially, there is a forward pass and a backward pass in the algorithm that keeps track of all of these estimates back and forth again and again. There are some results that show that essentially this is a faithful algorithm in the sense that whatever the fixed points that you get from this algorithm are actually critical points of the augmented Lagrangian of the original non-convex function. And if you're interested in what these dynamics actually are, they're related to some ADMM type algorithm called TRS ADMM. There are some open questions related to computational convergence of these algorithms. And this might be of interest if you ever try to take a look at those. But essentially, these variables R and beta are some kind of dual variables in the augmented Lagrangian that are also updated in a very specific manner using some ideas from belief property. The derivation is not important right now, but there is a multiplication by these matrices V1 and V2, which makes the analysis work for us. The multiplication by these matrices V1 and V2 in exactly this manner. So again, there is some kind of a result that shows that if you look at some average distortion between the estimator after t iterations of this algorithm for some intermediate layer in this estimation problem, with respect to the ground truth of that problem, then there is again this kind of deterministic behavior in this average distortion. So quantity on the left is again a random quantity. As p and n go to infinity, the quantity on the right is what they converge to, which is a deterministic quantity involving only scalar random variables. We know the formulae for these scalar random variables. They're complicated. but they're scalar is what's important. And this convergence actually applies rigorously. So we can, yeah, that's always an attractive property in any of these analyses. So in the interest of time, I think I'll skip some of the details of the assumptions under which this analysis actually holds. But essentially, these matrices B are assumed to be hard distributed random matrices.
So I'm a little bit perplexed here. What is Z0, Z1, Z2 for you? Is the output of different layers of neural network? What are you thinking here?
They're inputs to a neural network.
No, I mean, I understand the application of stat physics when you're trying to, decode codes, right? I mean, so their message passing is actually pretty clear. Right? You have these different observations. Based on that, you are coming up with log likelihood, right? And then you are based on the connection, basically the Tanner graph that you have, you can sort of do message passing, and you come up with more appropriate values of log likelihood. But I'm not understanding here what this graphs mean.
Right. Right. So there is a factor graph on these variables Z0, Z1, Z2, Z3.
Yeah. So what is this factor graph doing here? So there in coding problem is clear to me. What is the factor graph? What is the connection? What are you trying to achieve? Here is not clear to me. What is the objective function? What is it that you're trying to achieve?
You want to do map estimation.
Of what? What is the unknown here?
The unknowns are the quantities in red. The Z0,
Z0, Z1,
Z3.
Okay. And
the known is Y.
And why do you have like a sequential the Markov chain? So usually in the unknowns in the Tanner graph, right? Usually they have connection, but it's not clear that they are really sequential Markov chains, right? They have complicated connection with each other, right? And in every iteration of freedom. So I'm not understanding.
Right. So this is a specially chosen structure because it allows you to do analysis.
And how is it related to everything else you have done? I'm also not seeing that connection.
Right. So I have a slide that quickly just essentially. So essentially, when you're trying to analyze GLMs, these are your known quantities. The unknown quantity is theta. Okay. Now, when I explained what the data model was, that data model was effectively saying that X, which is your design matrix, is of this structure, and you can essentially write it in this manner. The transformation from theta to Y is exactly of this form. Now, when you do an SVD on Z, you see a similar structure where there are unitary matrices and element-wise operations happening. And similarly, the square root of the train covariance can again be written in this manner. So now you have exactly the chain structure that you can analyze. So you can apply the analysis framework directly.
Here you have a signal unknown, right? Theta.
Yes, you can introduce other unknowns along with it. You would throw them away when you are done with the analysis. But essentially, they are present. Those variables are present.
It's okay. I'm not sure I understand. But yeah, sure. Go ahead.
Okay. Yeah. So the summary essentially is that we have a framework that allows us to do an exact analysis in high dimensions. And when we apply that framework to get a handle on what generalization error looks in problems like GLMs, we get very accurate answers about what you should expect of these estimators on finite sample systems under certain randomness models in the analysis. And this helps us in understanding several effects of the different design choices that we need to make in GLM estimation. Specifically, what is the effect of over-parameterization, effect of the regularization, effect of distribution mismatch, and how things degrade as you change the distribution mismatch. In non-convex problems, the initialization also helps us. We can also analyze the effect of initialization on the non-convex problem solution. And yeah, the really nice thing is that this is not dependent on convexity at any point during the entire analysis. And so it helps us analyze statistical estimators which are non-convex.
So one question, in the message passing algorithm, to analyze the convergence of that algorithm, like when does it converge? Does it converge always? Or?
Right. So convergence of those algorithms is has not been universally proven. It has been proven under some sufficient conditions. So yeah.
Essentially, when they converge, they are converging to the stationary points of your problem.
Correct.
In some sense, I mean, you are trying to solve the equations which can give you the critical points.
Correct. Exactly.
Rather than solving the optimization problem by taking a gradient or whatever.
Correct. Correct.
Is that at a broad level? Is that what is that?
Right. Exactly. So this is an iterative way of understanding what are properties of those critical points of the augmented Lagrangian. But because there are no guarantees computationally on when these optimization algorithms will actually converge, you might be better off using other optimization algorithms. But you can use this algorithm for the purpose of analysis.
But if it doesn't converge, then how do you use it for the analysis? You can't guarantee the convergence of the algorithm.
You have a result about the asymptotic convergence of the algorithm. Right? You have this holds for every t, right? Now, what you are really interested in is what happens when t is infinity on the left-hand side. Okay? And that's exactly what happens when t is infinity on the right-hand side. So, you can use this. You can simply work with the right-hand side with only scalar random variables and do the analysis and get some fixed points over scalar objects. And those will be your potential solutions to what happens to those critical points. Because the non-convergence also happens because of numerical problems that we face. But this is this result holds rigorously. So you can just work with these scalar objects and see what happens at convergence. Sorry.
Any other questions? Any question from online audience?
Is there a question there?
No.
Okay. Thank you, Dr. Pandit, for an interesting talk. As discussed before, we would like to remind the audience to subscribe to our YouTube group for information on future talks. You can also visit our website for more details. Thank you and have a great day.